I should have had my laser pointer on. That's always good to point at stuff. I will revisit cosmological redshift, which we introduced before the break. Again, we'll talk about also what I introduced earlier, is the difference that we need to separate motion through space from the actual expansion of the universe and expansion of space. And then we go into the topic of how to define distance, and then some consequences of that. So what we need to discuss is how to find distance at the largest scale, how that relates to what is observable as the cosmological redshift, and then what do we mean with distance? There are different definitions clearly coming up about distance in expanding space. So to go back to cosmological redshift, because this is an extremely important observable, and we really need to understand the very basic principles of what it is. It's not a Doppler effect. Like if you observe shifts of spectral lines in the nearby universe, like the Andromeda galaxy is blue shifted. Okay, you can say that's a Doppler effect. Andromeda is coming towards us, bingo, that's it. But if you look into, observe into deep space, you are talking about redshift that is a cosmological phenomenon, cosmological redshift. Sometimes they say that photons are stretched. Sometimes in publications, it's a crazy concept. Photon is a fundamental particle, and we don't even know what a particle is. Modern scientists refer to particles as fields, vibrations, and then say that the particle can be stretched is a bit far-fetched. But I mentioned the wave, if you consider photons or electromagnetic radiation as a wave phenomenon, then the distance between two crests, adjacent crests of the wave or troughs, that's what we call wavelength, that is increasing while the light is traveling over billions of years through space. In general relativity, I use the term proper for certain features, and in this case, we talk about proper distance between the two crests, which is the wavelength, and the more or less relativistic proper way to say this is that the proper distance between two crests of the wave, or the proper wavelength, you could call it, is increasing. And that's because of the fact that the universe is expanding. Leave it at that, okay? But we have a redshift happening strictly because the universe is expanding and that light is traveling over such long periods of time. And in a sense, it tells you how much redshift you observe. That means how long these photons have been traveling. This is basically the shortest way of addressing what you're actually observing. But as I mentioned before, we need to plug it into a whole cosmological model, and it is just one of the essential parameters that we can put in. And this one is observable, which is fantastic, to really understand how it contributes to our whole understanding of the expanding universe and the history of the universe. This animation here I showed you before is really very illustrative. The longer the light travel, the more redshifted it becomes. It gives information about the geometry, space-time, the expansion history, and also the value of H0, which is the current expansion rate. So we can observe it. That's why this is such an important concept. And here I mentioned this before in the context of the Laniakea research, Laniakea supercluster, the definition, where they use the watershed principle. If along one line, stuff is moving in one direction, and on the other side of the line, it's moving in the other direction. That's the watershed principle. This is how they define the boundary of what is called the Laniakea supercluster. In order to do this, I mentioned this in the previous lecture, we need to, of course, we observe the redshift, but that is a combination of, at this distance scale, this is clearly a combination of the actual radial velocity compared to us, and on the one hand, and on the other hand, the expansion of space that you're also observing. What they undoubtedly have been doing in this research is that they took all the observations and then they applied a model, a cosmological model, essentially just Hubble's law with a value for the slope of the line. And then they said anything at this distance will have such velocity because of the expansion. At this distance, it has another velocity. And they subtracted then these velocities, these radial velocities, from the observations. And this is how they got what they wanted is the actual, what we call peculiar velocity, that is the motion through space. If you observe nearby, like the Andromeda Galaxy, or even in our local group, kind of, maybe the Virgo cluster even, you hardly have any effect of the expansion, if at all. It just drowns in the effect of the actual motion through space. If you look really far away, the actual motion through space hardly matters anymore. It's all the Hubble flow or the expansion of space that you are observing. It's the in-between range. This is an example of it, where you need to do your utmost to separate those two. So here we have a list of types of distance that are being mentioned. Some are more important than others, and some of these are only important in a certain context. I'll kind of come back to that. Yeah, I will come back to that for sure. Let's go along the list. Naive Hubble distance. That is really naive because what you say is we have Hubble constant, it's the slope of the line. So I can, if I measure a certain velocity, it's the vertical component, I go to the right where it hits the line, go down, and I have the distance. That would be valuable, correct, if everything else in the universe would have been constant, of this expansion was totally constant and has been the same forever and ever. No changes whatsoever, just that expansion. So that's why it's called a naive measure of distance. Light travel time is almost a direct consequence of the cosmological redshift. It's the time that photons have been traveling. So it's actually not a distance measure, it's a time measure. But if you multiply that with the speed of light, you get the distance to the object. But this is important, the distance to the object at the time that the light left that object. The light that we are observing now, today, in our telescopes. Because the space is expanding, that object will be much further away over the time since the light left the source. Because of the expansion of space, that the distance has increased significantly. I'll give you an example. We'll later talk about the edge of the observable universe. That's an event horizon. This is currently estimated to be 13.8 billion light years. But this is if you take the light travel time, multiplied by the speed of light, which means that's the distance of that edge, that event horizon, as it was when the photons from that horizon left the source, which we are now observing so many billions of years later. So that's light travel time. And the related version of distance. The key thing is the distance to the object where that object was at the time that the light left it. And then we have co-moving distance, which is the other side of that story. That is the distance to that same object where it is now while we observe these photons. This is a line of sight or co-moving distance. This is actually the most accurate form of distance. Not accurate, it has nothing to do with accurate, it's principle. It's the most logical definition of distance in an expanding universe. How far away is that galaxy or whatever now when I receive the light? So that's the difference between light travel time distance and co-moving distance. And then you have something called angular diameter distance, which is not a standard candle, but it's called a standard ruler. It is only used in the context of the cosmic microwave background. I'll mention this probably briefly when we talk about this very important radiation, where you have in the whole field of the observations that you do, you have certain features that have a certain size, an angular size. And then you can basically do the very simple geometry. If you know the actual size of the object and you measure the angular size, then that has a geometric relationship with the distance. And then you have something called luminosity distance, which is not used very much, or if at all. This is where you say, well, you can use it as a standard candle, like we do, for instance, for the Type 1a supernovae. But then at extreme distances, even if you would know the luminosity of a certain phenomenon, this is affected by, for instance, dust in the universe, extinction, dimming of light. So you make systematic effects if you would use luminosity as a measure for distance, even if you would know luminosity. So basically what it says is that the standard candle technique doesn't work really well at very large distances. Anyway, this is an overview of the various types of distances, and this gives you an idea about how they deviate from each other. These are graphs I got from Wikipedia, which I think they're illustrative. But you need to understand the left side is a linear scale in redshift from 0 to half. And here you have redshift in a logarithmic scale, going all the way up to 10,000 here. Crazy. So this graph fits in here until 0.5, which is somewhere here. This is a logarithmic scale now. So this part here, that is basically this graph here. So you see that roughly until a redshift of half or so, it doesn't really make that much difference which of these definitions you're following. But if you go beyond, and you have a significant redshift, there's a strong deviation of some of these definitions. The angular diameter is completely collapsing, measures distance far too short. The naive Hubble just keep going. That's why it's naive. So at long distances, that's giving an overestimate, a huge overestimate. Even worse is the luminosity method. The two which are most realistic is the look-back time. That is the travel time multiplied by the speed of light. That kind of tees off asymptotically to a constant. So this is a relatively good measure for distance. And its component is the line of sight co-moving distance, which is the distance where the object is now if you have applied the expansion history of the universe over the time that the light has been traveling. But those are the two definitions of distance that are most sensible in cosmology. I just wanted to give you that illustration to summarize that list of different possible definitions of distance. Here we have a very interesting calculator. First of all, I need to go back to the lecture, to the handout. I really want to do this with you, at least briefly, and then you can play around yourself. So this is the handout. I'll go to this practical here. I need to move it out of the way temporarily. to go back to my lecture. That's here. So let's go to that website. This is a calculator, which a cosmologist called Ned Wright has put up. It's fantastic because this is so illustrative, even for us lay people, to look at this cosmological model that I will unravel in the next courses, in the next lectures. But how that relates to this one concept of cosmological redshift, how that affects the different definitions of distance. So I have so many windows open, I need to make some space here. So here's a question. Suppose we have observed a quasar that has a cosmological redshift of 7.03. Using the calculator, find out the light travel time and the co-moving distance. You leave all the other values the same. So 7.03 for the Z, for the redshift. Remember that? So I put in here, this is the Z, 7.03. I leave everything the same, and I click on flat. I'll explain later what that means. And here you have a light travel time of 12.954 billion years. So here's the handout. Oops. 12.954, you see? Because you put in the Z here, 7.03. What is the co-moving distance? Well, that's here, co-moving radial distance is 28.795 billion years. So that's where if that's a quasar, for instance, that is where that thing is now, at the distance where it is now, because of the expansion of space. And there's another practical, which I just leave to you for you to do. But go to if you feel like you want to have some practice here, then go to the handout and do this yourself. The key thing here is that you see that there are several other parameters here. You have the H0, we know what it is, that's a Hubble constant, it's a certain value. If we would change that value, like let's make it 7.2, I click again on flat. Now look at the right-hand side here. For instance, light travel time 12.9454 it was. What it becomes is now 12.522. But there's a change. The omegas I will talk about next week, and when we talk about the cosmological model. These are very important parameters. This is the redshift. Then you have another omega. So, and then the universe is either open or it's flat. It's a choice here. So this is a very concentrated version, if you wish, numerically, of the cosmological model that I will explain in the next lectures. The cosmological redshift is only one parameter of it. The Hubble constant is also one parameter of it. That's what I meant before, that you need to put those parameters into the black box, which is the cosmological model, to get a conclusion of what it means. In this case, I'm talking about those two kinds of distance. But you can also see that the age of the universe at that redshift, how long after the Big Bang that was. So there are different pieces of information here. Also luminosity distance, completely crazy. Angular size distance. So you see those different things that we have talked about, how they are affected by a certain value of redshift that we observe in the context of the whole cosmological model, including those other parameters. That's the message I want to convey to you. Okay, I hope that you that makes sense. So I'll leave that, for the rest, I'll leave that to you. So that's what I mean here with this slide. See the workout examples, and this link gives you the access to the calculator. Okay. Now, if you want to measure distance, as you see, you just have seen, that is dependent on the model. If I change the Hubble constant value, if I change one of these omegas, I will talk about later what that means, or an open and a flat universe, then the results change. So that's the effect of the model. So we are totally dependent on that whole model to interpret redshift as a measure of distance. It would be fantastic if we have an independent way of finding distance related to a certain redshift. And there are a few of those. So that gives you a model-independent way of interpreting distance. Examples are those three, but I'll talk about. I'll only mention them basically because there's very little to talk about. This is way above our pay grade, above my pay grade. This one is relatively recently understandable. That's gravitational time lensed time delay. I have talked about the bending of light in space. It's what Einstein predicted. We very often in deep space images, we see these ring shapes. This is basically one object which is hidden behind a concentration of mass. Usually that's a cluster of galaxies in the foreground. And we see the light of the distant objects, which itself we cannot see, along different paths that are going past this, that are bending past that gravitational lens, as it's called. So if you look at the light in this part, because this whole ring is clearly the spread out image of one object. If you see a temporal variation, like a light curve, quasars, for instance, they are variable sources. They have distinct features in their light curve. If you see such a feature happening at one point, this is a shorter trajectory past the lens, so that is observed, and then you wait till you see the same feature in that light curve coming from the other side of the ring. That's what you would find here. And then what you can measure is the time delay of that one feature. Now, the interpretation is actually quite straightforward. If you look at the geometry of this line here and this triangle here, you measure basically the difference in length between this distance and this distance. And if you do some geometry, this difference gives you a measure for the distance to the foreground object, which is still far away. We talk about 1 billion light years or something. That's the lensing cluster. So you can measure the distance in this way, or calculate the distance, measure based on the measurement of the time delay. This is basically what it means to do gravitational lens time delay. And they do this. That's because you see those effects very common in deep space images, and that's when you can apply this technique. This is a very complex technique. I'm not going to discuss it at all. He's a famous Russian cosmologist. I'll talk about him later in the context of cosmic microwave background. This is a picture of the cosmic microwave background radiation. I haven't discussed this at all. I will later. But there are certain angular features that you can observe that are affected by some hot gas in galaxy clusters between that radiation and us. So the light is affected. Now, well, that's a very complex astrophysical theory, but that would be an independent way of measuring this. That's all I'm saying. Gravitational waves is a new kid on the block. It's a very important, potentially very important contributing observation to observation technique to cosmology and astronomy in general. What we can do, but sadly those events that we observe are not very common, but we have observed a gravitational wave, which must have been the result of a merger of two neutron stars or even black holes. I can't explain how we know that, but it must at least be a very powerful event if we see that space-time itself is vibrating and we can observe that. It's amazing that we can do this. And then in the same direction, this gives a direction where that event happened in the past. And if we look, in some cases, we can find a gamma ray burst, for instance, in the same direction. And then we can relate those two. That's a godsend if that happens. The gamma ray burst is electromagnetic radiation. That gives us a measure for the redshift, cosmological redshift. The gravitational waves observation gives us an estimate of the distance. So here we have redshift and distance related. And this is completely independent of the cosmological model. So that's a fantastic feature. But it's only happening every now and then and completely chance. So we can't dictate those events, of course. Some comments about the observable universe, and we have talked about this before. I mentioned it. There is an event horizon. Now let's go into that. We know that the age of the universe is finite. It has started at some point. We also know that the speed of light is finite. It's pretty fast, but it's finite, and especially at these extreme distances of billions of light years. That light takes billions of years to get here. Of course, that the fact that it is a finite speed is a very important factor. Which these two observations, they mean that there must be a phenomenon which is so far that the light that it has emitted, has not had yet the time to arrive here. It's still on the way. So there's no way that we can observe that. Because we have to wait. Maybe we have to wait 1 million years, and then we suddenly see it. Because it is 1 million light years travel time further than that event horizon. So there is and that's why we call it an event horizon. It's not dependent on your technique, your technology, how good you are in measuring distances or receiving light. No, there's a dark, the universe is dark beyond that event horizon, where you have a combination of the age of the universe and the finite speed of light. So there's no way that we can have any observational communication with the universe beyond that edge. And that's why the term event horizon is a very good one. The universe can, I think I mentioned it last before the break. The expansion of the universe can be faster than the speed of light. It's a linear effect. The further you are, the faster it moves away. And at some point you reach the distance where the expansion rate is the speed of light or exceeds the speed of light. And that's totally acceptable because it's space. It's not the material object which is expanding. It is space itself which is expanding. So, and I'll come back to that, but this is the really important definition of the event horizon, which defines the observable universe. Currently, the edge is at a light travel time of 13.8 billion years. But that means this was the distance to that event horizon at the time that the light left. Because the age of the universe is 13.8 billion years. Light that has been traveling over that long time has just had enough time to reach us. But anything that emanated from a source which was further away at the time that it left, than 13.8 billion light years, didn't have the time to reach us yet. But if you think about the co-moving distance, which tells you where that object is now, so where is the event horizon now, when over all these 13.8 billion years this universe has been expanding, the calculation is that it is 46.5 billion light years. So that's the difference, is how much the universe has been expanding over the lifetime of the universe. I hope that makes sense. If you read somewhere in papers, and you hear that in a lecture or something, that people say the diameter of the observable universe is 90 billion light years. That's where this comes from. 45. If you round it up to 45 and you take double, because this is a radius, then you have the diameter of the observable universe. Beyond that, light hasn't had the time to reach us yet. Okay, so this is a really hardcore limitation to what we possibly could observe. Again, totally independent of our technology. We will never be able to observe anything that's further out, unless we wait. But we can't. If you wait 1 million years, then this becomes 1 million, which is the third decimal, because this is billions of years, more. So instead of 13.800, it would be 13.801. Third decimal, yeah. That's 1 million years. So in 1 million years from now, we have a slight increase of that observable universe, that bubble that we can see. So this is really important to get your head around, because that's a fundamental limitation in what we can ever observe. And it also gives you a good idea about the difference between travel time distance and co-moving distance. I mentioned those two as the most important distance measures that we define in an expanding universe. Okay, this is another concept. I mentioned this actually already. That's referred to as the Hubble horizon. That's much closer. That's at the point where the receding velocity, because of the expansion of space, starts to exceed the speed of light. You can calculate this for yourself. If you have a value for the Hubble constant, and you say that's constant over all this time, take 68 kilometers per second per Mars, a megaparsec. I think in the handout I'll have done that calculation, but you can do this almost here by looking at it. At 1 megaparsec distance, that's what this means, this Hubble constant. The galaxy recedes at 68 kilometers per second. At double that, it recedes at double that, of course. Now, when do you reach the speed of light, which is 300,000 kilometers per second? It's a fairly simple mathematical problem. You just crank it out of your calculator. The distance here will turn out to be 4,412 megaparsec. So if you observe an object at this distance, then because of the expansion of the universe, the redshift will indicate the velocity will be the speed of light. Anything further will move faster than the speed of light. Again, this is no contradiction with general relativity, totally, perfectly acceptable, because it's space itself that is expanding. This is about 14 billion light years. That is the radius of that Hubble horizon, if you convert megaparsec to light years. There are other horizons, and that's it's getting more complicated if you look into different definitions. But I'll give you a taste of that in the handout if you are interested. But stick to the previous one. This is really the important thing, is that we have a limitation, a fundamental limitation, due to the fact that the age of the universe is finite. It started at some point, and the speed of light is finite. Those two combined give you that distance to what we call the event horizon, and that defines the size of the observable universe. And you can look at it in two ways. You can look at it in light travel time, and you can look at the size of that bubble at the present time, how much that is. So this is really interesting consequence of thinking about distance in an expanding universe. So this is one additional horizon, and there are more in the handout, as I say. These are all centered in our personal point of view. So what would an alien in a galaxy far, far away observe? Well, they are in the center of their bubble. So if that alien is really far away, that alien will be in the center of its own bubble. And if you're not too far away, or if that alien is not too far away from us, these two bubbles will overlap. And that overlapping parts of the universe, this is, if we ever could communicate with those aliens, that is the stuff that we can communicate about. Hey, we observe this there. Yeah, I can see that too. This is just theoretical because you have to communicate over extreme distances. But just making the point that we will share an observation space with aliens if they are not too far away. But if these two bubbles are further away, the centers of these bubbles are further away than the radius, than the event horizon itself, and the radius is the same for that alien as it is for us, because the alien lives in the same universe with the same age and has to deal with the same limitation of the speed of light. When these two bubbles are not overlapping, even if we could communicate, we have no sensible way of sharing information about the universe. For them, the universe is a different place than for us. It doesn't need to be physically different, but it is a different volume of observable space. This is what I'm trying to explain in the context of this event horizon, the observable universe. So I hope that that is clear now. I mentioned this several times before, but now we have the opportunity to really clearly define what we mean with observable universe. Okay. So we're reaching the end here of this discussion. Very interesting question is, what is beyond? But there is no way that we can find an answer. We have no observational connection beyond that event horizon. This is the reason why we call it an event horizon. So you can have any kind of ideas about this. That's fine. But there is no, what you could call, there's no causal connection. We cannot observe events that are related to something that's further away. Very likely, there is much more universe beyond that horizon. There are even ideas that the universe could be infinite. There is no limit. It could still have started in the Big Bang. There's no contradiction there. Maybe I'll come back to that in the next few lectures. I can't recall if if I bring that up, but otherwise you can ask. But for now, this is a reality that we have to accept, that there is no way that we can know anything about the universe further out than the observable universe. The whole consequence of having an observable universe, a limited observable universe. Okay, so this was a really important, more or less practical lecture discussing practical consequences of the fact that we live in an expanding universe. Because you need to be careful with how you define distance. And I've given you several definitions. The most important one are the light travel time distance and the co-moving distance. But if you want to calculate the distance from observations, for instance, the observation of cosmological redshifts, as I've shown you in this practical, and I hope that you will find the time to go back to that, you will see that you need to plug that into the whole model that I'm going to explain in the next weeks, in order to relate that to distance in either of these definitions. This is really why I emphasize that practical that I have showed you. And I also encourage you really to find some time in the coming week to do this practical yourself, so that you can really understand that it's a collection of parameters, which is called the cosmological model. That is where it's like a black box. You just put a value in, other values are in there already, and then you can get something like distance or the age of the universe or so as an answer coming out of it. So cosmological redshift, the value of the Hubble constant, these are inputs into that black box. They are not in their own right giving you immediately a distance. For instance, cosmological redshift. It doesn't give you the distance straight away. You need to plug it into this model, and then you can get sensible outcome. This is really where we are going, and this is what I needed to explain beforehand, before we really go into the details of that cosmological model. So that's that's basically what I wanted to say in this lecture. We are doing very well in time because it's comfortable that I even before 9 o'clock I finish this. Okay, next week we are going to talk about the cosmological model. This is the deep end of the swimming pool. I don't want to scare you, but I'm just saying. I'm trying my best here at Big Bang Cosmology, this lecture here. I'll start with a brief history, but then you need to realize that general relativity is the foundation. This is how Einstein came up with his mathematics, and that is the foundation for what we now call cosmology. If you haven't done so before, I've made that recommendation several times, is to go back to the previous course and review the theories of relativity. I had special lectures on this. This is the lecture Special Relativity, the first one, and that's the General Relativity lecture. I really encourage you to at least briefly go through that this coming week, so that you come prepared that if I say this is general relativity, the bending of space-time, bending of light, curvature of space-time, those concepts, that makes sense to you, that it's not completely new. So this is really important that you provide that basis for yourself in order to have the benefit of the lecture for next week, which is this one here, Big Bang Cosmology. Whew, there was a lot of discussion. We have really entered cosmology now. We do live in an expanding universe. We are making observations that make lots of sense, but also we have a lot of problems. And it all relates to how we put things together in that model, which we refer to as the cosmological model. And that's where we're going next week.